So we're going to look at hypothesis testing using normal distribution today, okay? It's going to cover a couple of new things, and there's going to be a bit which confuses probably a few people, but I'll try and hopefully get you guys following along as much as possible, okay? In the exercise in the book, on page 285, it's talking about some guy in Sydney and some woman as well, I think, as well. The guy's making a claim that the air pollution in Sydney is getting worse. The woman wants to test his claim, so she takes a sample. I think that's what is actually happening. And it gives you a whole scenario, blah-de-blah-de-blah, blah-blah-blah, okay? But more importantly, when we move on to the other side, and we talk about the data, in fact, it's on the other side. Yeah, okay. When you take your data that is collected from a sample, okay, guys, back. When we take our data, our sample, when you find the mean of your sample, that is purely an estimation of your population. Okay, this is kind of what I talked about, I think, yesterday, slightly. So when we do our mean of the values that was collected, we get 331. That is purely an estimation of our population mean, okay? If you were to take another sample, would you expect that mean to be kind of close? If you took another sample of 10, would you be expecting to be roughly around 331? Yeah, okay, because every sample should roughly be around the same mean. Would you expect it to be exactly the same? No, okay, you would expect some difference within it, okay? So every time you take a sample from a population, you get different values. They should be relatively similar to a certain degree. And actually, one of the things we'll talk about is how if you are to take a distribution of a sample means, okay, if you take means of a population, you keep doing means of a population, your sample mean distribution should be kind of normally distributed. But that's something I think we look at a bit later on. Although they do kind of show you an example of it down at the bottom of 286 with that graph. They said, if we did the sample size of 10 1,000 times, this could roughly be what our distribution of those sample means would look like. But again, like I say, that's something we're going to look at later on, okay, about sample mean distributions. The key thing, though, is on the other page is there's a couple of new things, okay? When we do our normal distribution of a sample, so normal distribution of a sample. So if you've got a normally distributed set of data, your sample distribution you'd expect to be normally distributed. Does that make sense? So if your original data is normally distributed, if you do a sample distribution, you would also expect it to be normally distributed. That's what they're showing with a diagram there. The green line represents population distribution, the red line represents the sample distribution. Is that all right? Cool. Your n slightly different. So you know how it's normally mean and variance, okay? So we've still got the same mean, still got the same population mean. However, our variance is now sigma squared over root n. Okay? So our mean, we don't really have any change to our mean. However, our variance, we need to account for the fact it's a sample. And the way to account for it being a sample is we're going to divide our variance by root n. N obviously representing the number of pieces of data, okay? So if it's a sample of 10, you do root 10, okay? Oh, sorry, over n, sorry, not over root n. It's the standard deviation, which is over root n, sorry. Yeah, as pointed out, the standard deviation then would be sigma over root n, not sigma squared over root n, that was my mistake. So that's basically it, kind of. We need, whenever we do a normally distributed question based upon a sample, the first key thing you've got to remember is you need to divide your variance by n, which means you're dividing your standard deviation by root n. Okay? So if you look at the example at bottom, it says Ama Williams, I'm not sure who that is, believes that the carbon dioxide level in Sydney has risen above the usual levels of 328 parts per million. A sample of 10 specimens of Sydney air are collected with the carbon dioxide level within them is determined. The results are as follows. So they give us a set of data. Extensive previous research has shown that the standard deviation of the levels within such samples is 2.5. So for this example here, we know our standard deviation is equal to 2.5, and that the distribution may be assumed to be normal. So we know that our distribution can be assumed to be normal. Okay. The results are as for, use these data to test at a 0.1% significance level. So sig level 0.1%. Ama's belief that the level of carbon dioxide at Sydney is above normal. Okay, so we've already done hypothesis testing. If I was to draw a distribution, okay, we've got our distribution, looks something like that. Okay, we're saying that it's increased. So is it one-tailed or two-tailed? One-tailed, because we've got a given direction, it's just increased. It's not just, it's changed in some way. It's specifically increased. So our H0 will be mu is equal to 328. Our H1 is going to be mu is greater than 328. Okay. Obviously, guys, what do we need to make sure that we do in our actual test? Write it in context, yeah. So say what that means in context. So the mean carbon dioxide level is 328 parts per million. The mean carbon dioxide is greater than 328 parts per million. I just don't want to spend my time writing that down right now. Okay. So this is our normally distributed graph. We've got 328. We're testing at 0.1% significance level that's greater than 328. So what region am I looking at? Am I looking at the higher end or the lower end? Higher end. So I'm going to drop a thing. What's my significance level? So that is equivalent to my probability level as well, which is 0.1%. Okay. So this is kind of roughly the distribution I'm looking at. There's 3 different ways of finding the, hypothesis testing here. Okay. 1, we find the probability of our mean, which I think is 331. So we find x bar is 331. So we find the probability of x being greater than 331. That's one way of doing it. Okay. Using your standard deviation, using your distribution tables, we can use that. Does that make sense? Find the probability that x is greater than 331. Are you okay? Because the 10 means added together and divided by 10. 10 values, yeah. Yeah. It is on the previous page, we calculated it for us, so I just took that value. Okay. So, yeah, is everyone okay with the sample mean? X bar, remember X bar represents a sample mean, that's what we discussed yesterday as well. Is everyone okay with X bar being 331? Yeah. Yeah, cool. Right. So we can find the probability of the event being greater than 331 by using our distribution table. So you do 331 minus your actual mean, which is 328, over what? 2.5 over root 10. Okay, so remember, this is what I was saying a second ago. Standard deviation. If they give you standard deviation, which is 2.5, you now need to put that over your sample size, square rooted, so root 10. So that would give us a z value. You can use that to find phi z, and you can compare. Okay, whatever that phi z value is, we compare to it. So actually, this is the method 2 that's described in the book. So it's on the next page, method 2. So you end up with a z value of 3.79. when you look up 3.79 in your thing, you get phi z as 0.99993, okay, which would represent the lower end of that. So you need to do 1 minus for your probability x is greater than 331 is equal to 1 minus 0.99993, which is 0.00007. So is that significant enough? What level are we testing to? 0.001. Okay, because it's 0.1%. So because 0.00007 is less than 0.001, then you can reject, null, accept, alternate. Does that make sense? It's the exact same thing we did with binomial. Yeah? No? Or maybe this is why question 5 went so poorly in the test. Okay.
Well, are we doing the method 2?
Method 2 is currently what I'm referring to, because method 2 is the one that kind of fits in with what we've already done.
Wait, why don't we... Wait, never mind. Wait.
Francis?
How do I look up 3.7?
Oh, it's not there. Okay, so in the real test, your z value should actually appear. Okay, but this z value is so big that it doesn't tend to appear. If you notice, 0.007 is like 0.007%. Okay, so small, so insignificant, never likely to appear. That's why it's not appearing in your z table. I think what z only goes up to 3, doesn't it? Yeah, goes up to 2.999. Okay, so there's other ways that you can do this. Okay, in the real test, hopefully they won't give you a z value which is so big that it doesn't appear on the table. It's just the textbook doesn't care about that. They're just, yeah, because the z values do carry on. They do carry on. I'm sure somewhere you can find out all the z values up to a certain point, but it becomes so insignificantly small that they just stop eventually. But that's one method of doing this. Find the probability of this happening and compare it to the significance level. Okay, so let me just write that down as a thing. Find the probability of the event happening, of the event compared to sig level. Okay, so that's one of the 3 methods that you can use to do this. Okay, another method, which is, I think their method, no, in fact, I'm going to use their method 3, because method 3 is closely related to method 2. So method 3 says, once I found my z of 3.79, I can stop. Okay, I don't actually need to use the table to find out the probability. I can stop at 3.79, because if you look at your formula sheet, there is a special table at the bottom. Okay, the special table at the bottom is about the specific probabilities for significance levels. Okay, so if you look at the special table at the bottom, if we're doing a 1% significance level, okay, 1% sig level, one-tailed, okay, so we need to make sure that we understand what that means, one-tailed, then you can compare that to 0.1% significance level, then you can compare that to the 0.99 p-value, which generates a z value, okay? What's the 0.99 p-value that generates a z value? 3.090, okay? So once I got my z value here, 3.79, I can compare it to 3.090, okay? So because 3.79 is greater than 3.090, I can reject my null hypothesis, okay? Because my value that I've got is so many standard deviations away from my mean, it is considered significant enough, okay? If it was 3 standard deviations away from my mean, it wouldn't be significant enough because I need it to be 3.09 or more standard deviations away from my mean to be considered significant. Question?
So, in the exam, can you use either way, or will they tell you what way to
All right, so in an exam, certain ways might be more better for like part 2, part 3. Okay, depends on the situation. But any method used to test for hypothesis, any one of these 3 methods, will be accepted. It's just that maybe in part 2 you'll have to do an extra calculation that you could have already done in part 1 without realizing. Okay, so to put this in a diagram perspective, if this is 3 to 8 and this is 3, 3, 1, okay, that is 3.79 standard deviations away, okay, from the mean. Okay, 331 is 3.79 standard deviations away from the mean. If it was the crit standard deviation is 3.090 standard deviations. Okay? So anything greater than 3.09 standard deviations away from the mean, that's what Z is actually calculating, by the way. That's what Z's calculating, is the number of standard deviations away from the mean you are. Anything greater than 3.09 standard deviations is within my crit region. Okay? My rejection region. Okay? Where I would decide to get rid of everything. So that would be my rejection region there, which 331 would fall within. Okay? So that's method 3. Like I say, it's very much related to this method. It's just at the Z value, you can stop and compare on your table. Is that all right? Yeah, does that kind of make sense? Right. The last method, and this method is one which can sometimes help with part 2s and part 3s, I think a bit more than the other 2, because this one will allow you to find your type 2 errors and type 1 errors. Sorry, your type 2 errors. Okay, this is the crit value method. So it's labelled as a big old X, generally. Yeah, critical regions. Yeah, okay. So basically, method 1 in the textbook is saying, rather than using the 331 and finding the probability, use the probability to find a crit value and then compare 331 to the crit value. So it's very similar to method 3 as well, because you take your distribution, you use your 3.09 standard deviations, and then you use your 3 to 8, to find what the crit value there is. Okay, so it's reversing the normal distribution formula. Okay, so we got the 3.090 from our table. Yep, they've used that one. Okay, you take the 3.090 from the table and you say that is Z. So Z is 3.090. So 3.090 is equal to our unknown value minus your 3 to 8 over your standard deviation 2.5 over root 10. And you rearrange this to find X. Okay, so 3.090 times 2.5 over root 10 plus 328 is going to equal your X value. Is that all right? Which they find out to be 330.4. So because 331 is greater than 330.4, reject, null, accept, alternate. Because that value there is 330.4. Anything greater than that value means you reject your null hypothesis. Does that kind of make sense? So it's very similar, again, with a binomial, it's kind of similar to finding the crit value, you know, where you had to keep going until that percentage was below, okay? However, here, you don't need to do that. You just use the Z value from a table and rearrange the formula to get the crit value. So it's a bit quicker than binomial. Because binomial, you keep adding more and more and more and more to it until you find that value that is significant enough. Here you go, well, I know the significance level. I can just plug it into this formula and generate my crit value. Okay, this is good for when you want type 2 errors as well. Because if you then know your crit value, you use your crit value to compare to another value for type 2 error. In the same way you do the crit value compared to another value for your type 2 errors with binomial. Okay, but you guys will do some more questions on this before that starts to make sense, because that's a lot of information just there. Okay, so yeah, the last step would be to say, because 331 is greater than 330.4, reject null. Okay, so they're all methods which end up with the same answer. They're all valid methods. The first one is the one which you would have done from last year. You know, find that probability. It's just find that probability and now compare it to a significance level. Method 2 is, don't worry about using my table to find my probability. Just look at that Z value and compare it to that critical Z value. Okay? It's a bit quicker. It saves you about 30 seconds from actually finding in the table what 3.79 would be. You know, time is money. Sure. The other method is, I know how significant I want to test myself to. What value would be that point? What value would be significantly far enough away from my mean before I can start rejecting things? Okay, it's finding that crit value. Okay, those are the three methods. Okay, that's kind of all I really want you to focus on today. I think they do go into a second thing about BATS as an example. Same process. They talk about the type 2 error in there. I might save that for later. Yeah, because I don't want to do that. I want you to do some questions. I don't think there's anything else which is new. Oh, estimated variance. All right, okay. If you want to estimate your variance, guys, so you might not be given the standard deviation. Okay, so if you are... Yeah. Okay, so this is 292. Okay, you just need to know a new formula. Okay, so if your overall population standard deviation or variance is not known, okay, assuming you've not been able to make that calculation, how do you find a variance from the sample? Okay, so the variance from a sample is defined as S squared, because it's our sample variance. It's the formula on the thing. And it's 1 over n minus 1 times sigma x squared minus sigma x squared over m. Okay, so let's break it down. If I had some numbers, 3, 4, 5, 6, my sample's 5, okay? So using this formula, I would say S squared is equal to 1 over 4, okay, times by my sigma x squared, so I would need to square all of these, so 9, 16, 25, 36. Sigma x squared means to add it all up, so 9, 16, 25, 25 is 75, plus 36 is 111, okay, minus sigma x, all added together, so 3, 7, 12, 17, 23. So that's sigma x, that's sigma x squared, which is 23 squared over my n, which is 5. Yeah. And that gives you your estimated variance, okay? So that's an estimated variance. Whatever that is, you'd then use that to find your standard deviation by just square rooting it, whatever it may be. And then you divide that by root n for your actual use of normal distribution. Okay, so if you look at the example there, they've used the values that have been given. I think they actually gave him sigma x and sigma x squared. We didn't actually have to calculate it. It was just plug it into the formula shape. 1/149 times their sigma x squared, which is stated in the question, minus their sigma x, which is stated in the question, but then squared, divided by 150, equal 224.998, which means the standard deviation is 15. So when they did the normal distribution, they did 15 over root 150, which is their standard deviation divided by root n. It's on the book, not on the board, so it might be better to look there. Okay, right. So that was that last example. Have I got some questions?